All right, welcome to the third page. We really talked about the top of this already. But here we're going to talk about the superposition principle of homogeneous equations. All right, the superposition principle of homogeneous equations states that, okay, if we have more than, one solution to our homogeneous nth order differential equation, all right, and on some interval I, then we have another solution to our homogeneous equation by taking a linear combination of all of our solutions to our differential equation. So again, say we had y sub 1, y sub 2, all the way up to y sub k, solutions to our homogeneous equation, then we always have an extra solution to our homogeneous equation by just taking the linear combination of all of our solutions to the differential equation. So y sub 1 plus y sub 2 plus y sub k multiplied by some c1, which these are all going to be some arbitrary constants. All right. So let's see how that actually works. So say we are given a differential equation a of x, y prime, y double prime, plus b of x, y prime, plus c of x, y equals 0. So it's homogeneous because we have a linear differential equation that's set equal to 0. Let's say we have two solutions. Say y1 and y2 are solutions. Y sub 1 and y sub 2 are solutions. That's a horrible, solutions. All right, now what we're going to do is, if those are solutions, then what we can say is that we have, let me write this in a way that you can be able to read it. So a of x times and y sub 1 double prime plus b of x y sub 1 prime plus c of x y sub 1 will satisfy our differential equation. And so when we plug y sub 1 in, we're going to get 0. Now say we do the same thing, but now we're going to do it with y sub 2. Set that equal to 0. And so say, okay, if they're solutions, and when we plug them into our differential equation, we're going to get 0. Now, if we do a linear combination of this, say, we add these two solutions together. So we can just add that, and we can multiply by, we can say we'll multiply that by c sub 1, and then we're adding these two equations and have c sub 2. So then what it would look like would be this. I'm just going to write it all the same color now. C sub 1, a to the x, and then I'm going to combine my, right, so here, let me write it this way. All right, we'll have a sub x times c sub 1, y sub 1, double prime, plus a sub x, c sub 2y double prime, plus b sub x, c sub 1 y sub 1 prime plus b sub x c sub 2 y sub 2 prime plus c sub x y sub 1 c sub 1 y sub 1 plus c of x c sub 2 y sub 2, and all that equals 0. Now what we can do is we can pull out our a of x, and we're going to be left with c sub 1 y sub 1 double prime plus c sub 2 y sub 2 double prime plus b of x times c sub 1 y sub 1 prime plus c sub 2 y sub 2 prime plus c of x c sub 1 y sub 1 plus c sub 2 y sub 2 equals 0. Right, now for derivatives, we can go ahead and just pull the derivative out because of addition is not going to bother any other scalar multiplication. So a sub x is going to be c sub 1 y sub 1 plus c sub 2 y sub 2 double prime. Alright, because that's the same, we took the derivative. And when we take the derivative, we'd only be taking the derivative of y sub 1, y sub 2. That c sub 1, c sub 2 are just going to be constant, so they're not going to be changed. That's why we're able to do that. I'm going to do the same thing, c sub 1, y sub 1, plus c sub 2, y sub 2 prime, plus, and then we're left with c sub c of x, and then c sub 1, y sub 1, plus c sub 2, y sub 2, and that equals 0, which shows that the linear combination of y sub 1 and y sub 2 are also going to be solutions. So what superposition means is that if y sub 1 and y sub 2 are solutions, then also we can say so is the linear combination c sub 1 y sub 1 plus c sub 2 y sub 2 is a solution to our homogeneous differential equation. All right.